In this section, we're going to be looking at the cross product of two vectors. First, we're going to talk about how we find the cross product and then understand what the cross product actually means and how it might be used in some applications. One easy application is what's called the area of a parallelogram. But using the cross product, we also find an orthogonal vector to two given vectors. So we're going to start by a definition that allows us to calculate the cross product. Later, we'll describe the properties and how we can use it. Now, the formula I'm going to give you here is actually not the way that I recall or remember to find the cross product. It comes from another representation that we'll describe on the next page of this lecture, or of these lecture notes. But let's start by just writing down an algebraic formula for finding the cross product. If you have two vectors, and they have to be three-dimensional vectors, so a1i plus b1j plus c1k, and w is a2i plus b2j plus c2k, then the cross product, denoted by v cross w, is as follows. It is b1 times c2 minus b2 times c1 as the x component. The y component is a2 c1 minus a1 c2, and the k component, the z component, is a1 b2 minus a2 b1. Trying to find a pattern among that is going to be a little bit challenging. There's some patterns there, and I'll encourage you to kind of think through how you might remember that, but the truth is you don't actually have to, because there's another way we're going to write down this formula later on that helps you remember it much easier. This is also sometimes referred to as the vector product. So let's just use this formula as it appears now to find v cross w. So v cross w is, you take, remember this is a1, b1, c1, and a2, b2, c2. Order matters for this to get the right answer, and we'll show that later on. This does not commute the same way that the dot product does. So take b1, which is a -4, times c2, which is 1, minus a b2, which is 2, times a c1, which is 2. That's all times I. Plus, now take a2, which is 3, times a1, which is 1, minus, and now take a1, I'm sorry, I said c1, I didn't say the right thing. You take a2 times c1, which is 2, and then you take a1 times c2, so minus a1, which is 1, times c2, which is also 1, that's times your j, plus a1, which is 1, times b2, which is 2, minus a2, which is a 3, times b1, which is a -4, all times k. All right, so this becomes -4 minus 4, which is a -8i, plus 6 minus 1, which is 5j, plus 2 minus a minus, because we're going to have a negative, 2 plus 12, which is 14k. All right, so -4 minus 4 is -8, 6 minus 1 is 5, and 2 plus 12 is 14. This is the vector product. Now notice one thing different about vector products is the output is a vector. With dot products, the output was a scalar, and a scalar whose application we covered in earlier lectures. We haven't yet covered what this vector actually means, but that's how we find the cross product. So note, just to reiterate, this is a second way to multiply vectors. The dot product, or scalar product, gives a scalar as an answer. And the cross product, or vector product, as we've also called it, gives a vector as an answer. So an easier way to remember the formula for calculating a cross product or vector product of two vectors is to use something called determinants. Now, you may or may not have seen determinants earlier in your mathematical school or classes, mathematical schooling. But they do show up when you're talking about linear systems. They are a very useful way to identify properties of a linear system, properties such as whether or not it has a solution or not. There are also some techniques using determinants to help you solve 2x2 systems and 3x3 systems. So let's start by just defining what we mean by a determinant, or at least how we calculate a determinant. So a determinant is something that acts on a matrix. It's a formula or a function that depends on or has as an input a matrix. A matrix is just a rectangular array of numbers. So let's think of an array as having rows and columns. We've got a 2x2 matrix inside here, meaning it goes 2 this way and 2 this way. They have 2 rows and 2 columns. So if you remember this formula, the rest of what we're going to show you is going to be a piece of cake. The determinant, which the way you can tell I'm asking for a determinant is you get vertical bars on the outside of this rectangular array, that is this square of numbers. When you put vertical lines on the outside of it, you mean find the determinant, and the determinant is A1B2 minus B1A2. And look at where that is on this picture. If I go forward, that's A1B2, right? So that's positive. And if I go backwards, that's a negative. Because we're going backwards, we're going to say negative. That's B1A2. A1B2 is the forward diagonal. B1A2 is the back diagonal. And so anytime you want to find the determinant of a 2x2 matrix, you take the forward diagonal minus the back diagonal. Forward diagonal minus backwards diagonal. Okay, so now a 3x3 determinant can be done a number of ways. But there's a shortcut for you to remember the 3x3, and it's still the same idea of forward diagonals and back diagonals. The formula is actually this. It's A1B2C3 plus B1C2A3 plus C1A2B3 minus C1B2A3 minus, and I'm going to have to change lines here in a second. Let's do B1A2C3 minus A1C2B3. Now, where did I get those numbers or those terms, right? If I took all this product and then added them up as I've got them here, I end up with what's called the 3x3 determinant of the matrix. So the easy way to remember this formula is by the following notations. First, rewrite the first 2 columns of that 3x3 array. So take the first column, this column here, and rewrite it right next to it. And then take the second column here and rewrite it here. And just leave off the third column. You don't have to write it a second time. Now take the forward diagonals. What are those? Those are A1, B2, C3, B1, C2, A3, and A1, B2, and a C1. Or actually, I should have written that in the same order that it goes. It's a C1, A2, B3. C1, A2, B3. You add all those up. And where do you notice those? These guys are right here. Boom. And now do the back diagonals. I'll just do this in red so you can see them this way. that would be C1, B2, A3. You're going to subtract that because we're going back, and you do A1, C2, B3. That's subtract also, and then subtract the next one, which is B1, A2, C3. Those three terms, C1, B2, A3, right there. B1, A2, C3, right there. And A1, C2, B3, right there. Forward diagonal minus back diagonal. So the same thing I wrote up here. Forward diagonals plural minus backwards diagonals. Now let me point out that if you move on from this course and you end up ever someday in a linear algebra course, I need you to remember one thing, that these are shortcuts, and these are shortcuts that only work for 2x2s and 3x3s. When you start talking about determinants in a 4x4 and higher, this trick doesn't work. So, but fortunately for this class, all we need to define the cross product is the 3x3 determinant. All right, so A and B in my examples are 2x2, so it's going to be forward diagonal minus the back diagonal. All right, so that's 2 times a -1 minus a 3 times a 4, which gives me a -2 minus 12, which is -14. That's the determinant. So at this point, we're not doing anything with vectors right now. We're just kind of learning what determinants are and how we calculate them. Second one, same thing. Forward diagonal minus back diagonal. 1 times 1 is the forward diagonal minus a -1 times a -1, which gives me 1, because 1 times 1 is 1, and -1 times -1 is +1, so 1 minus 1 gives me a 0. In linear algebra or in solving linear systems, when your coefficient matrix has a determinant of 0, things are bad. That matrix is called singular. You don't have a solution, or you don't have a unique solution to that linear system. We don't need to know that now, but I thought I'd throw that in just as a kind of alluding to what you might be able to use determinants for later on. Now, let's do the last one. Forward diagonal. Actually, first thing, what did I tell you to do? I told you to rewrite the first two columns. So 2, 1, 1, and -3, 0, -1. Now I'm going to do a highlighter instead. Let's do the forward diagonal. Boom, boom, boom here. Boom, boom, boom here. And boom, boom, boom here. So what do you get? You get, grab the right pen, 2 times 0 times 2 plus -3 times 2 times 1 plus 4 times 1 times -1. And now the back diagonal, which I'll do in, let's say we'll do that in green, this way, and this way. So that's 4 times 0 times 1. Remember, you subtract the back diagonals. And then minus 2 times 2 times -1 minus -3 times 1 times 2. All right? So 4, 0, 1, 2, 2, -1, and -3, 1, +2. And forward was 2, 0, 2, -3, 2, 1, and 4, 1, -1. Now we do just some arithmetic. That's 0. -3 times 2 times 1 is -6. 4 times 1 times -1 is a -4. 0 here, so that's a 0. 2 times 2 times -1 is 4. A negative and a negative make a positive, so +4. And -3 times 2 is -6, and a minus times a -6 makes a +6. -6 minus 4 is -10, plus 4 is -6, plus 6 is 0. The determinant of that 3x3 matrix was 0. Now, where the cross product comes into play is, you can see it in the theorem below. What we do is we place two vectors on the bottom two rows and put the unit vectors in the x, y, z direction as the first row. So we need to be able to find determinants if for example, we have variables involved. So let's do this example D and then take a look at the formula for the cross product and where it shows up. All right, so do this, we end up with rewriting A, 2 and 1 here, and B, 3 and 2. So the forward diagonal are these guys. You have A times 3, which is 9A, and B times 5 times 1 is 5B, and C times 2 is plus 4C. And now if you do the back diagonal, which we'll do in green again, you get minus C times 3 times 1, which is minus 3C. And then A times 5 times 2 is minus 10A. And then minus, because we're going backwards, is minus B times 3 is minus 6B. Which gives me 9A minus 10A is negative A. 5B minus 6B is negative B. And 4C minus 3C is plus C. Minus A minus B plus C. By the way, one of the things you can do here to kind of shortcut this is you could do this here when you have a variable on top, and then this here, if you subtract those two immediately, that would be 9A minus 10A. You can combine those right away. Then if you did the B's minus the B's, and then you did the C minus the C, then you can write down immediately this answer, almost to the point that you could do most of it in your head. All right, now the claim is that the cross product, which was this lengthy formula way up here at the beginning, remember this formula right here, can be represented simply by this formula right here. The determinant, that those two formulas are in fact identical. And here's the proof of that. Let's do I, J, K, A1, B1, C1, A2, B2, C2. So to calculate that, I will rewrite the first two columns, I, A1, A2, and J, B1, B2. So I'm going to come down here and just going to do this all in one fell swoop. So let's do the forward diagonal of the I minus the back diagonal with the I in it. What does that give me? That gives me a B1 times C2 times the I minus a C1 times the B2, all times the I, right? It's because you would get B1 C2 I and B2 C1 I, and you're subtracting the back diagonal from the forward diagonal, which is exactly, and I'll just scroll us back up here to see it, is exactly what I had right here. B1C2 minus B2C1. B1C2 minus C1B2, or B2C1. Now let's do the J's. So let's do this one right here minus this one right here. That would be plus a C1A2 minus an A1C2 times J. I think I have A2C1 up there and A1C2 up there, right? A2C1 minus A1C2, exactly what we expected. Boom. Okay? And then last of all, do the K. So this guy right here, minus, if I go the back diagonal, that would be plus, the forward diagonal was A1, B2, and the back diagonal would be a B1, A2. And then the K factored out. And there's the formula, so proved. It's exactly the same thing we had above. So instead of having to write down that whole formula every time or memorize that formula, what you really need to do is just remember this right here. That's the trick. And where do the vectors go? If you're going V cross W, the V is the second row, the W is the last row. The first row is always IJK. All right, so let's go ahead and do this using the new formula. I have I minus 4 plus 2, I minus 4j plus 2k. I have W is 3i plus 2j plus k. So the cross product using the new formula would be the determinant of I, j, k, and then take the components of v, the first vector, and put it on the second row. 1, negative 4, and 2. And then the second vector, put that on the third row. 3, 2, 1. So I'll rewrite I, 1, 3, and j, negative 4, 2. And now I'm going to do the forward diagonal with the i's in it and the back diagonal with the i's in it. And that gives me negative 4 times 1, right, which is a negative 4, and 2 times 2, which is 4. So negative 4 minus the back diagonal, which is 4, all times I. And now do the j. Here's the forward diagonal with the j in it. Here's the back diagonal with the j in it. You've got 2 times 3, which is 6, minus a 1 times 1. So that's times j, plus, and now do the k. 1 times 2 is 2, minus a negative 4 times 3 is minus a minus 12, or plus 12k, which gives me negative 8i plus 5j plus 14k, which, by the way, these are the same two vectors I used earlier. I got negative 8, 5, and 14, which is exactly what I got. Where was it? Negative 8, 5, and 14. All right, right back down here. Sorry to keep scrolling up and down. I hope I'm not making you nauseous. What happens if I do W cross V? What's the difference if I switch the order that I'm multiplying by? Well, it's certainly different in the formula because I have to do I, j, k. I have to put the first vector on the second row. So I have to put a 3, a 2, and a 1 here. And I have to put a 1, a negative 4, and a 2 on bottom. All right, so let's see what happens. If I do I, 3, 1, and j, 2, negative 4, the forward diagonal is with the I here, and the back diagonal with the I is here. I end up with, for my I, 2 times 2 is 4, minus a negative 4, which makes it plus 4 for the I. If I do the forward diagonal for the j and the back diagonal for the j, I've got 1 times 1 minus a 3 times 2, so that's a 1 minus 6 times the j. And do the forward diagonal for the k, and here's the back diagonal for the k. The forward diagonal is negative 12 minus the back diagonal, which is 2. Okay, so you end up with 8i minus 5j minus 14k. Notice it's not the same vector. It is the negative of the vector. So note, in this case, v cross w was a negative of w cross v. The negative being that operative point that goes in the opposite direction. And the reason is, what has happened is you switch the order of these, right? You switch the order of these. When you swap the rows, you switch the order of the subtraction, which is basically taking a negative of a subtraction problem. Last interesting thing to note is what happens if you take a vector cross with itself. V cross v is going to be, you put a 1, a negative 4, and a 2 here, and a 1, a negative 4, and a 2 here. And you do I, 1, 1, and j, negative 4, negative 4. If you do the I forward diagonal minus the back diagonal. What do you get? You get a negative 4 times 2, which is negative 8, minus a 4 times negative 2, which is minus 8. Negative 8 minus a minus 8. If you do the forward diagonal for the j, you get, this is plus here, forward diagonal is 2. The back diagonal is also 2. 1 times 2. 2 minus 2. J. And last is the k, so I do the forward diagonal with the k in it and the back diagonal with the k in it. So you get 1 times negative 4, which is negative 4, minus a negative 4 times 1, which is a negative 4 again. So what I get is negative 8 plus 8, which is 0, plus 2 minus 2, which is 0, plus negative 4 plus 4, which is 0. What I get is the 0 vector. And in fact, that's a property that we're going to see turns out to be true anytime you cross a vector with itself. So now let's look at the properties of the cross product. And the properties of the cross product will help us understand what it actually means. What does that vector that we get as an output have to do with the original vectors that we started with? So the first thing I want you to just notice is how it relates algebraically. So these are the algebraic properties. Things like commutativity, associativity, distributions, those sorts of things. If you take a vector and cross it with itself, as you saw, you'll get 0. And if you take a vector and cross it with another vector and then try to switch the orders, you get a negative when you switch the order. Right? So this is called non-commutative, because you do not get the same thing if you cross them in the opposite order. Distribution rules, the associativity rules hold. If you do a scalar multiple of a cross product, you can do a scalar multiple of the first vector and cross it with the second, or you can do a scalar multiple of the second vector and cross it with the first, again maintaining the order, first cross with the scalar multiple of the second. You can also distribute vector products or cross products across addition. So u cross v plus u cross with w. So in that sense, because it's a distribution rule, it behaves like you would expect multiplication to behave. The second set of properties is what really gives us more information about what this new vector actually means. These are called the geometric properties. Now, I'm not going to prove these for you. I'm going to state them without proof, although there's some information given in your text to support each of these claims. First of all, u cross v is orthogonal to both u and v. And in fact, the way that it is orthogonal is if you think of two vectors. Here's u right here, and here's v right here. Let's say these things are lying in some common plane. There is, if I go straight up or perpendicular to that plane, this right here is the u cross v. It is a vector that is perpendicular to both of them. If you take any two vectors, you can place a plane that contains those two vectors, and then the cross product is going to be perpendicular or orthogonal to that plane. So it's orthogonal to both u and to v. Additionally, the magnitude of that vector can be found using the magnitude of u times the magnitude of v times the sine of the angle between them. Now that's kind of a out of left field formula, but it is in fact true. How long this vector is has to do with the sine of the angle between them. I don't know if you recognize this. This is actually half of an area formula that we recognize. If you think of u as the length of this side right here, magnitude u, and magnitude v is the length of this side right here, if I were to draw a triangle by drawing a line straight across there and calling that theta, the area of that triangle would be 1/2 magnitude of u, magnitude of v, sine of theta. 1/2 AB sine theta. That's a formula for area that we learned back in the triangle lectures. Right? So this is not half of it, this is two of those together. And in fact, where you can see that it's two of them, or I guess where would the second one be that makes up the difference, is if I were to draw a parallelogram that is giving one side parallel to the u and another side parallel to the v, notice how I've got two of those areas. If you take two of them, you get this guy right here. So that right here, this formula, is the area of the parallelogram, having u and v as adjacent sides. So we can find the area of parallelograms in the plane by simply using cross products and then taking the magnitude of the cross products to do so. So that's one of the homework examples we're going to be looking at here in just a second. Last thing, if you get 0 when you take the cross product, either they're the same vector or they're parallel. This last point here just says if you get 0, the only way that that's possible is if the area of that parallelogram is 0, and the only way for that area to be 0 is if the two angles, or the two vectors, go in the same direction, namely that they are parallel. So how do we find a vector that's orthogonal to two given vectors? Okay, just another way of asking for u cross v, or v cross w for that matter. If we find u cross v, we are going to find an orthogonal vector to both u and v. How do we do that? We put I, j, k as the first row in a 3 by 3 determinant, 2, -3, 1, and -3, 3, and 2, and I, 2, -3, j, -3, 3. So we do the forward diagonals with the i's in it, and the back diagonal with the I in it. We end up with -3 times 2, which is -6, minus a 3 times 1, which is 3, all times I, plus forward diagonal for the j, and the back diagonal with the j in it. Gives me 1 times -3 is -3, minus 2 times 2, which is 4, for j, plus forward diagonal for the k, backward diagonal, so that's 2 times 3, which is 6, minus -3 times -3, which is 9, positive 9k. I get -9i minus 7j minus 3k. That vector is orthogonal to both of those. Now, how would you show that it's orthogonal? Do you remember from the dot product section, the way that you show two things are orthogonal is taking their dot product, right? So what happens if I do this vector right here crossed with u? That is, let's take 2, -3, 1, dotted with -9, -7, -3. What happens? That's 2 times -9 plus a -3 times a -7 plus a 1 times a -3, right? So that's -18 plus 21 minus 3. You get 0. That's a check that this is orthogonal. If the dot product is 0, they are orthogonal. You can check and do this with v as well, and you'll see that you'll get, in fact, 0 if you dot my answer with the original v. That's another verification that we found the vector that's orthogonal to both of them. At this point, we have 3 points given to us. P1 is 1, 2, 0. P2 is -2, 3, 4. And P3 is 0, -2, 3. We want to find the area of the parallelogram where one corner is 1, 2, 0. That's P1. And the other, from P1, we have two adjacent sides. One going from P1 to P2, and one from going from P1 to P3. Now, what does it look like? And, of course, I'm not going to draw this very accurately because this is going to be in space. This is not even in two directions. But we've got a P1. We got a P2. We got to say a P3 out here. Okay, in fact, let's put P3 over here just to get more parallelogram looking shape. Again, I'm not actually graphing these in 3 space, I'm just graphing them for our own illustrative purposes. If I call this vector right here u, and I call this vector right here v, then this parallelogram has an area equal to the magnitude of u cross v. It's one of our properties of the cross product. So how do I find u? If u is P1, P2, then I'll take P2's components minus P1's components. A -2 minus 1, a 3 minus 2, and a 4 minus 0. Right? This minus this minus this, and this minus this, which gives me -3, 1, and 4. V would be P1 to P3, which would be P3's components minus P1's components. So 0 minus 1, -2 minus 2, and 3 minus 0, which gives me -1, -4, 3. So this vector, I'll highlight them, this vector here and this vector here are these two vectors on that side, or those sides of the parallelogram. So now we got to find u cross v. So I'll use my determinant formula for that. -3, 1, 4, -1, -4, 3. Put an I, -3, -1, and a J, 1, -4. The forward diagonal minus the back diagonal for the i's gives me 3. Oh, come back. 3 minus a -16. Forward diagonal for the j minus the back diagonal gives me 4 times -1, which is -4, minus -3 times 3, which makes a -9, j, plus, and we'll get k. Forward diagonal for k is 12, minus the back diagonal for k, which is a -1. So that gives me 3 plus 16 is 19i, plus -4 plus 9 is 5j, plus 12 plus 1 is 13k. So the magnitude of u cross v is the square root of 19 squared plus 5 squared plus 13 squared. So scroll that down a bit. 19 squared is 361, plus 25 plus 169 is 13 squared. Add those up. 361 plus 25 plus 169 gives me 555. All right, so the square root, 555, is approximately equal to 23.6 is the area of that parallelogram. So that's how we apply the cross product in a couple of examples. Now there's a whole world of applications beyond what we're covering in this course, and you'll see them if you ever end up in a calculus course where you're looking at multiple variable functions, or in a linear algebra course, but this lays a foundation. But notice how it's also built on your trigonometry understanding, where you're talking about direction angles for vectors. That's what we've covered there. We also have this formula that came from the area of a triangle, magnitude of u, magnitude of v times sine of theta, which gave us the information we needed to be able to determine that, yes, in fact, this does form the area of a parallelogram. All right, so that's the end of this lecture series. Thank you for participating. Thank you for watching. And I hope you have a whole world of trigonometry applications open up before you. This is Dr. Franklin with Wayland Baptist University signing off.